Hey there, ladies. Today we're going to talk about 6.1 graphing linear inequalities. For those of you who are in class, we started talking about a little bit, but we didn't quite get through the lesson. Just a forewarning that this lesson is going to be a little bit longer than our normal go-to, because we would have probably done this over the course of 2 or maybe even 3 days. So keep in mind that this video is going to be quite lengthy. Which means that if at any point you feel like you've had enough math for today, or for even just a little bit, you need a break, just pause the video, go do what you need to do, come on back, because I'm just going to do it as one giant chunk. So, first starters here, we're going to talk about graphing linear inequalities, which means you should probably know what a linear inequality is. A linear inequality is similar to a linear equation, except there's not an equal sign there. It is a relationship between two linear expressions in which one expression is less than, greater than, less than or equal to, or greater than or equal to. So instead of an equal sign, we've got those symbols instead. Okay. When we're dealing with linear inequalities, we deal with them in a very, very similar manner than how we deal with linear equations, except there is one exception, and that exception is when multiplying or dividing both sides of an inequality by a negative number, the direction of the inequality changes. All right, so when dividing or multiplying both sides of an inequality by a negative number, the direction of the inequality changes. Notice how it only says multiplying or dividing, and it has to be done to both sides. So if we have something like adding 3 or subtracting 3 to both sides, that doesn't change anything at all. It's only multiplying or dividing, okay? So below we have an example where we could see that happening. So if we're wanting to solve for y here, we are trying to get y on one side and everything else on the other. So if we're taking a peek, the first thing that we're wanting to do is we're going to get rid of that -7. To get rid of -7, we're just going to straight up add 7 to both sides. When we add 7, our inequality does nothing. Nothing changes with it because we're not multiplying, we're not dividing, and it's not a negative number. So we end up with -3y is less than 6x plus 15. So nothing fancy, nothing changes. However, when we get to this point here to get y alone, we are going to divide both sides by a -3. And when we're dividing both sides, that's every single term on both sides here. So those 3's cancel out. Oops. Those -3's cancel out. We left with y. And because we divided both sides by a negative number, what happened here? Boop. We get y. And because we divided both sides by a negative number, our inequality changes from a less than symbol to a greater than symbol. It just changes direction. Okay? And then we are left with 6x divided by -3, which is -2x. And positive 15 divided by -3, which is -5. So our final answer, or final isolation for y here, is y is greater than -2x minus 5. So notice that is the change in direction of the inequality because we divided both sides by a negative number. So what we're going to be talking today primarily is actually graphing equations with linear inequalities. The nice thing about that is very similar to graphing lines like we did in 6.0. The major difference is that inequalities will have more than one correct solution. They will have a whole solution set. So to define a solution set, just change back to my blue here, the solution set is the set of all possible solutions. So every single possible solution in a linear inequality belongs to something called my solution set. So as a really, really basic example here is if I had the equation x is equal to 3, my only value or only possible value for x would be 3. Whereas if I said x is greater than 3, I have oodles of possibilities for x, right? X can be 3.001, x can be 4, x can be 547, right? X can be a wide variety of answers and still have that become a true statement. So all of those possible solutions is part of something called my solution set. Okay. What we have below is the graph of 3 things. The first one here, is an equation, right? There's an equal sign there. The second one is an inequality, and the third one is also an inequality, right? So here we have an equation, and here we have an inequality, and here as well. What we might notice between the two of them, so if we're looking at equation and we're looking at inequality, the first thing that might jump out to you is that inequalities have this shaded region, okay? So here, in this inequality, we have this whole region that's shaded, and same with this one here. We have a whole region that's shaded, and we don't have any of that nonsense up in that equation, okay? So when we're talking about inequalities, we are going to have a shaded area. And what a shaded area does is that it represents the values included in my solution set. So that shaded region represents every single possible value. So if I'm looking at my last one here, y is greater than 2x minus 7, this point is a solution. 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 Every single data value within my shaded region represents a solution in my solution set. Okay? Can I do that? There you go. All right. Another thing you might realize is if I zoom in here, we see that this line is dashed, this line is solid, and this first line is solid, right? So what does the last one have that the first two don't? And what you might notice is that when I'm looking at my signs in the middle, this includes equal to, this also includes equal to, but this one does not. It's just strictly greater than, okay? So I'm going to have two different possible lines. I'll have a solid line if my values on that line are included in my solution set. And we'll just quickly wipe this out here. Get rid of this Miss Thibodeau. And we will have a dashed line. Oh, that's much thinner. This one? Oh, that's way too thick now. Whoa, ho, ho, ho. If my values on that line are not included in my solution set. So the main difference between an equation and an inequality are these two things. First of all, inequalities have shaded areas that represent their solution set. Okay, that's the main difference that we could see jump out at us right away. The second difference is the solid or dashed line business. It can be either or depending on the inequality sign that we have. right? If the inequality sign has an equal at the bottom, then all is good. We include a solid line. If that inequality doesn't have an equal at the bottom, then it's not going to be part of our solution set, so we use it or indicate that using a dashed line. So on the next page here, what we are going to do is we're going to show you tell you the exact 3 steps on how to graph a linear inequality. Okay, the 3 steps are kind of wordy, so you might not want to write too large, but I promise you that they'll be a lot easier when we put them to context rather than just writing them out. So if you don't totally get it just by listening to me here, I promise you once we start doing an example, it'll start to make a lot more sense. So we have 3 steps. Step 1 is that we are going to graph the boundary line. And if you notice in the graphs on the previous page, they all had lines that had the exact same shape, the exact same slope, they had the exact same intercept. Actually, I'll go back a little bit here. If you notice that for each of these graphs, they have the exact same intercepts, both the y and x, and they are connected with straight lines. Whether they're solid or dash doesn't matter right now. But the fact that they have the same line, that line is called a boundary line. And so that's our step 1. That's what we're attempting to graph here. Okay, and we graph it just like we normally would for an equation. So if we have y is equal to mx plus b, our b is our y-intercept, and then our m is our slope. We graph it the same way that we did in 6.0. The key difference in doing this for our linear inequalities is just determining whether it's a solid line or a dashed line. So the boundary line is going to be a solid line if the values are included. So that means if we have a less than or equal to symbol or greater than or equal to symbol, as long as that has that equal sign at the bottom, those are going to be included. We will have a dashed line. Or sorry, a solid line. Solid line if there's an equal piece at the bottom of our inequality. We will have a dashed line if the values are not included. So that will be when we have a straight up less than or a straight up greater than sign. No equals involved here. Okay. Our step 2 is then to find what region we're going to shade. Right, if you notice again on that previous page, I'll just scroll back a little bit, the second graph, the graph in the middle there, has the bottom right part of the graph shaded, and the graph at the end, graph 3, has the top left part shaded. How do we distinguish which is which? And that's our step 2. So we are going to use step 2 to find the region to shade. Okay. So when we're finding the region, there's a couple of things that we have to do within this step. So the first piece, or the first part, is to choose a test point. So we are going to choose a test point that is not located on our boundary line. So it can be on either side of the line as long as it's not on that boundary line itself. Ideally, if we could pick the point 0, 0, that makes the math really easy, because eventually if we multiply anything by 0, or we have 0, we divide it by anything, we are going to get a 0 as our answer. And dealing with zeros is really, really simple. But we can't always use 0, 0, right? If 0, 0 is a point on our boundary line, we cannot include it as our test point. But if we can, awesome. The next thing, once we've chosen that test point, is we are going to substitute the value, our values. That's kind of messy. Let me try writing values again. Values of our test point into the inequality. So if we have the inequality and we choose the test point 0, 0, our x, every time we see an x, we're going to plug in the point 0. Every single time we see the point y, we're going to plug in 0. And we are just going to straight up plug in those values to see what happens. If what happens, so if the test point makes the inequality true, i.e., it is a solution, then we will shade the test point region, or test point region. If the test point makes the inequality false, so it's not a solution, then we will shade the other region. And again, I know this kind of sounds a little bit confusing when we're not putting it in to an actual example, so the words kind of seem a little bit uncontextual. But as soon as we plug it in and start looking at our example, I swear it'll make a lot more sense. So if the test point makes the inequality false, so it is not a solution, then we shade the other region. All right, so step 2 is all about trying to find the region to shade. So we are looking for a test point that is not located on the boundary line. We are seeing if that test point makes the inequality true. If it does, we're going to shade that side of the line with the test point. If it is false, we're going to shade the opposite side, the side without the test point. The last step, step 3, tells us how we're going to shade the region. So this last step really just talks about what we're going to do in terms of given just straight up equations or given things like word problems. So if we are dealing with a function, if the function is continuous, which means all numbers are possible solutions, that means we're going to shade fully. So we're just going to straight up color. However, if the function is discrete, that means only specific numbers are solutions. Then we are going to shade and dot our region. So just for some context, continuous data or a continuous function is a function that could take on any possible number. So things like time is continuous because between 1 second and 2 seconds we have every single possible decimal that exists. But things when we talk about word problems like how many people can you choose, we're not having every single possible decimal place of people. We're only having whole numbers, right? We're having 0 or 1 or 2 or 3 or 4 or 5. So continuous, we will be dealing with continuous when we are just straight up given the inequality or we're straight up given the function. So if there is no context, there is no word problem in this unit, we are going to assume that everything is continuous. When we get to word problems, that's not always going to be true. So when we get to 6.3, when we get to 6.4, we're going to have word problems where only specific numbers are possible, right? Like maybe something along the lines of how many possible tickets could you sell for this show, or how many possible dollars could you make as revenue. That is going to be a discrete value because there's only certain numbers that are possible. You can't sell 8.347 of a ticket, okay? So these are the steps, and we're going to work through them in different examples, and I hope that as soon as we start going through these examples, it'll all make a little bit more sense. So I apologize if the definitions or the steps kind of don't, but I swear once we go through them, it should all connect a little bit better. So, first of all, let's pick a better color. I'm thinking purple. All right. So we have this inequality here. We have y is greater than or equal to 2/3 x minus 6. Okay. Taking a look at that, that is in a beautiful form that we can graph already. It's in the y is equal to mx plus b form. So there's the slope, the 2/3, and the -6, which is our y-intercept, which is absolutely fantastic. We don't have to do anything with the equation. So we can just go ahead and jump into our 3 steps. Our first step is to determine whether we're drawing this boundary line as a dashed or a solid line. Okay. We can see that we have the inequality, which is greater than or equal to. And since it's greater than or equal to, that's going to give us a solid line. Because of that equal portion of our inequality, because there's that equal at the bottom, our line is going to be solid. Okay. And we are going to go ahead, let me get my ruler here. And we are going to graph this. So just like we did in 6.0, we start with the y-intercept, which is -6. There we go. Our slope is 2/3, so we're going up 2/3, up 2/3, up 2/3, and then backtracking, so down 2, back 3, down 2, back 3. Whenever you are graphing anything in this unit, please make sure that your graphs extend past the edges of the graph. Because when we start dealing with word problems, it's going to be absolutely crucial that we see key intersections, we see where the graph exits the region that we are provided with. So please make sure your arrows extend past the edges of the graph. It is also useful to kind of continue on with the dots that I drew when I graphed, right, these guys here, just to make sure you're on the right track and your line's not kind of going off kilter down the road, because like I said, once we get to word problems, our accuracy matters. Okay? Not that it doesn't now, but it will matter more. That's our step 1. Our step 2 is to literally pick any point we want. So we could pick a point here, we could pick a point here, we could pick a point down here, we could pick a point up here. Because all we need to do is we have to pick a point that is not on the boundary line. So we cannot choose this point because that is located directly on the boundary line. That's our only restriction. Like I said in step 2, it is always easiest to choose the origin, our 0, 0 point, if possible, because it makes the math a little bit easier. So let's try that out for now. Let's try our test point is going to be 0, 0. Now that we've picked our test point, we are going to plug it into the inequality. And when we plug it into the inequality, we actually break the inequality up into 2 halves. We say what's on the left-hand side of the inequality and what's on the right-hand side of the inequality. That's what LHS and RHS stand for. Left-hand side, right-hand side. So on the left-hand side of the inequality sign, we've got y. And on the right-hand side, we got 2/3 x minus 6. What we are doing now is we are taking 0 and plugging it in every single time we see an x, and we're going to plug in 0 every single time we see a y. And we are going to try and get each side to be reduced to one single number. So on my left-hand side, I plug in 0 for y, I end up with 0, I'm happy. On my right-hand side, I plug in 0 for x, and I get 0 minus 6, which reduces to minus 6 as well. I'm happy because it is one final number. What I am going to do is I'm going to say, well, let's look at my original inequality here. My inequality said that my left-hand side, my y, should be greater than or equal to my right-hand side. Right? So I'm going to say 0 greater than or equal to -6. And that is actually true, right? 0 is a bigger number than a -6. So since that value is true, we are going to shade the region with my test point. So my test point was 0, 0, so I'm going to shade the region of the graph that has that 0, 0 as a test point. So I'm going to take out my highlighter here, and I'm going to shade it. So I'm going to go ahead and shade everything on that side of the line. Oh, that's weird that that happened. It doesn't have to be perfect, and I know some of you are going to be OCD and not want to go past the edges of our graph here, but the only reason that we're stopping at the edges is just because we didn't give you a bigger graph. But if we would have given you a bigger graph, you would have continued shading anyways, okay? So if you go outside the edges, that's fine. Just please don't try and do something like this, where you're very clearly going over that line. So please make sure you do your best to make sure that boundary line is not covered or crossed, but the edges along the graph, it doesn't matter as much. Our third piece is determine whether the function is continuous or discrete. And like what I said when we were writing out the steps, unless we have a context in which we have a word problem, or if we are given some sort of restrictions on the graph, which we are not given above, we are going to assume that all basic functions for inequalities are going to be continuous. It's not until word problems that we will see it be otherwise. Okay? So those are my 3 steps. So I've done a solid line because I had that greater than or equal to, that equal portion of my inequality makes it a solid line. I picked a test point, which is any point on either side of my line that is not located on my boundary line. I've plugged it into either side of my inequality. I wanted to check if that inequality was still true, which it was. 0 was in fact greater than or equal to -6. Because it was true, I shaded the region that included my test point, and because the data was continuous, or the function was continuous, I just straight up shaded fully. Okay. What we can do is we could actually see what that looks like on Desmos as well. Y is greater than or equal to 2/3 x minus 6. So if we take a peek here, and we look at our graph, we've got the same thing, right? We still have that that y-intercept of -6 and our x-intercept of 9, right? We've got that nice same line. Notice that in Desmos, the line is solid. There's no dashed there, okay? And we graphed or shaded the top left corner of it because that is where our test point made it true. And notice how I said that it doesn't matter if you go outside the edges because the graph would go on regardless. So if I keep on zooming out, my graph is still shaded. It doesn't end when my graph ends because realistically my graph never ends. It just continues on and on and on and on and on. Okay? All right. Next one. We're going to look at the next question here. And we have y is less than -2x minus 1. So again, we are going to start by graphing that boundary line. If we notice that boundary line is a less than, right? There's no equal to portion. So with that being said, we are going to have a dashed line because that inequality does not have an equal sign underneath. That boundary line is in the format of y is equal to mx plus b, which makes it super easy to graph. So I'm going to look at that -1 as my y-intercept. I have a slope of -2, so I am going down 2 and over 1, down 2 over 1, down 2 over 1, down 2 over 1, backtrack, up 2, left 1, up 2, left 1, up 2, left 1, up 2, left 1, up 2, left 1. And I'm going to connect it with a dashed line. Okay, so the dashes don't have to be a specific distance apart. It just has to be clear that that is dashed. And just like before, our line should extend to either side or past the edges of our graph. Okay? The next thing that we're going to do, step 2, is still to find our test point. And just like we said before, our test point could literally be any point that is not on our boundary line. So we could, in fact, choose 0, 0 all over again. That is a valid test point. But just to show you that it really doesn't have to be, I'm going to pick the test point here, 5, 4. Okay? Again, 0, 0 would suffice, but I just want you to see that it could literally be any single point and you'll get the same result here. So I'm going to choose a test point 5, 4. All right. We are now going to plug that into our inequality. We split that up into our left-hand side and our right-hand side. On our left-hand side, we just have y. And on our right-hand side, we have negative 2x minus 1. This time, when I'm plugging in values, every time I see an x, I'm going to plug in a 5. Every single time I see a y, I'm going to plug in a 4, because that's the test point I chose. So here I have y is equal to 4. On my right-hand side, I have negative 2 times 5 minus 1, which gives me negative 10 minus 1, which gives me negative 11. Now I'm going to see if my inequality is true. My original inequality said my left-hand side should be less than my right-hand side. Right? That's what we see up here. My left-hand side should be less than my right-hand side. So is 4 actually less than negative 11? Heck no, that is pure nonsense. That is false, which means we will shade the other region. Okay. Since we know that this is the test point that we chose there, it was our point 5, 4, we're not going to shade that side of the graph because the point came out false. It was not a solution. So we are going to shade this side over here. Ooh, but I wanted to do it in blue. All right, I'm going to shade this side over here. We're going to do the best we can not to cross the boundary line. Oh, so nice. And there we have it, nice and shaded. Our last step is to say, well, is this continuous? Is this discrete? What are we doing here? And like I said in the previous question, unless we're starting to talk about word problems, we are going to assume that it's continuous, so we are just going to shade fully. We're not doing any dots because there's no restrictions and there's no context to kind of limit us. So we are just straight up shading that region. We could still check our answer on Desmos as well to ensure that we're not crazy and we know exactly what we're doing here. And here we have it, if I just kind of zoom out here. We end up with the same coordinate points for our intercepts, right? Our y-intercept is -1, just as we graphed. Both of these lines are dashed, and our bottom left-hand side is shaded. Our side that does not include the test point 5, 4 that we would have chosen. Okay? Beautiful. So we could continue on here. I believe we have, what do we have? We have 3 more graph examples. We'll graph this next one together, but if at any point you feel pretty confident to move on by yourself, I strongly, strongly, strongly recommend that you go ahead, pause the video, try doing the next few on your own. Try a test point, whether that test point be 0, 0 when it doesn't belong on the boundary line, or really any test point you want that doesn't belong on the boundary line. And see what side you're shading. You want to get through and practice these on your own. Again, we will still continue doing these examples together, but if you want to press pause now or at any point and try the next one on your own, that would be totally recommended. All right, if you didn't pause, or if you did and you're coming back, welcome. We are going to continue on. So here, we want to figure out, is a solid line, is it a dashed line? We should be able to tell that it is solid because we have that equal portion of our boundary, right? We have that equal sign underneath our inequality. So we're going to have a solid line. Now, some of you might be looking at this and thinking, what the heck? How do I graph this? There's not a y in there. There's no y equals mx plus b. Well, excuse me. We are going to have a straight vertical line. So we'd graph it just like we would graph x is equal to 3. And that's by saying, well, what points are x is equal to 3? Well, x is equal to 3 here. It's equal to 3 here. It's equal to 3 here, so on, so forth. All these different points. I'm going to do a couple. I don't have to do every single one because I can see that that follows a pattern of an absolutely vertical line, and it's going to be solid like we said. So we are going to graph it as such. Our arrows are going to bypass the edges of the graph, and our life is going to be great. Next, we are going to pick a test point. So you notice that 0, 0 is not on the boundary line, so I'm definitely going to go ahead and pick that. 0, 0 is probably my personal favorite, not only because it makes the numbers easy, but it kind of looks like an owl. Ooh. Or a cat, depending what you think. But every time I see it, I think of an owl. So as long as it's not on your boundary line, you are safe, you are good to go. We're going to split this up into my left-hand side and my right-hand side. On my left-hand side, I just have x. My right-hand side, I just have 3. Which means every single time I see an x, I'm going to plug in a 0. Every single time I see a y, I'm going to plug in a 0. But in this case, we don't have any y's. So life is still good. So we're going to have 0 here, and our right-hand side is already reduced to a number there. So all we had to do was just figure out my left-hand side 0. I double-checked to see if this is a true solution. So my inequality states that my left-hand side should be less than or equal to my right-hand side. And let's see if it is. My left-hand side being 0 is less than or equal to 3. Well, that's true, because 0 is in fact less than 3. It is true, so we are going to shade my test point region, which includes my 0, 0. Okay. We are going to go ahead and pick a color. We are going to shade the region that includes this dot here, so the left-hand side of that vertical line. And here we go, across, doing the best we can to make do. And there we have it. Doing our best, we've shaded it fully. The last thing is, am I just leaving it as is, or if I'm adding dots in here? And like I said in every other example prior to this, it is continuous unless we start talking about word problems or we see restrictions indicated somewhere. So we are going to shade it fully. Similarly, like we did before, we could plug this into Desmos to double check we're good. So we have x is less than or equal to positive 3. And there we have it. It looks just like we anticipated. We have that positive 3 there, and our values are shaded to our left. So our shaded area, again, represents our solution set. From here, we've got 2 more. Whoop, whoop. The next one here is this guy. We are going to pick a different color. Maybe we'll pick, orange. Or if I'm going reverse rainbow here, I guess I should pick yellow. All right, so here we are. We have y is greater than -2. Our first step is to determine, is it solid, is it dashed? And from here, hopefully we can see that is going to be a dashed line because our inequality does not have that equal to portion at the bottom. When we graph this, we are finding the place where y is equal to -2. So y is equal to -2 there, or there, or there, or there, or there. Anywhere along this horizontal line, we get a value of y is -2. Remember that when we are drawing the line here, we are dashing it. Right? So again, your dashes don't have to be specific anywhere. They don't connect dots necessarily. It just shows that there's a dashed line indicating that our values on that line aren't included. It's just our boundary. But we're drawing it dashed. The next thing we got to do is we got to pick a test point. Test point. Whoop, whoop. When we pick a test point, it could be any point that is not on the boundary line itself. So any point that doesn't have a y of -2, because that would be located on the line. My go-to is there and ready for me. So I'm going to choose the test point 0, 0, because who loves it? Me. So when we're looking at this, we are splitting it up into my left-hand side. We are splitting it up into my right-hand side. My left-hand side just includes my y. My right-hand side just includes my -2. Every time I see an x, I'm going to plug in a 0. Every single time I see a y, I'm going to plug in a 0. Just because we don't have x's doesn't mean the world is going to end because we have a y. And we'll just plug in 0 here. And our right-hand side is all good to go. Our inequality suggests that our left-hand side, our 0, should be greater than our -2, which is our right-hand side. And that is in fact true, right? -2 is smaller or more negative than our 0, so this is a true statement. So we are going to shade the test point region. So the region with the 0, 0, which is what we chose as our test point for this question. We are going to, oh, I don't want that. I want this bright yellow. Oh, yeah. And we are going to shade everything that includes that point there, our test point of choosing. And we're going to go ahead and shade. And again, like I said, your graph doesn't have to be absolutely perfect. I'm not judging you on your art skills, just your ability to distinguish which side to color here. Okay. You should also be wary that you want to make sure that you're not shading past the line, so coloring between the lines is useful unless the between the lines are lines that really would continue if we had more paper. Okay, so we're going to show that on Desmos right after we figure out if it's continuous or not. And we know that it will be because there's no restrictions and this is not a word problem. So we're going to shade fully as we already have because it is a continuous function. So here we have y is greater than -2. And same idea. We've got the same y-intercept. We've shaded the proper region. Life is good. All right. We've got one more here, and this one's a little bit interesting. Not too insane in any way, but just kind of fun. We can see that we have this equation here, but the equation isn't ready for us to graph. It's not in that y is equal to mx plus b form, which is kind of a dagger, but nothing that we can't handle. Right? To get that over, to get the y alone, we're going to subtract 3 from both sides because we have a +3 there. Once we get rid of it, we end up with y is greater than -2x minus 3. Notice that we didn't flip the sign because we didn't divide or multiply by a negative. All we did is subtract, and subtraction doesn't do anything to our inequality sign. Only multiplication, only division. And now we just go as normal. So first of all, I look at my inequality and I notice that it doesn't have an equal portion at the bottom, which means we will have a dashed line because of that symbol, that greater than symbol. Not greater than or equal to, just greater than. We're going to go ahead and we are going to plot this line here, plot our points or plot our intercept, and then find the line. So we have -3 as our y-intercept, and our slope's -2. So down 2 over 1, down 2 over 1, down 2 over 1, and backtracking up to left 1, 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 up to left 1. And when I draw this line, we are going to do so that is dashed. Dash, 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 dash. And I'm going to make sure that my line extends past the edges of my graph because, like I said, it's going to be useful down the road. I also just noticed that I was going into reverse rainbow here, and now my question is green, and I'm so sorry. That bothers me too. Anywho, now we have to pick a test point, and if we're looking for a test point, check out that beautiful 0, 0 that is not located on my graph boundary line at all. Life is beautiful. So I'm going to choose it. Test point of 0, 0. And I'm going to break my inequality up into a left-hand side and a right-hand side. Boop, 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 boop. Left-hand side, I like to use my original equation, so I like to use the y plus 3 version, but you could totally use your rearranged version as well. So you could use the OG one, or you could use this one when determining the left-hand side and the right-hand side. I personally am a fan of using the original just so that if I made any mistakes down the road, at least I could pick the right side to shade. But again, up to you. Here, my right-hand side will then be -2x. I'm going to plug in a 0 every single time I see an x. I'm going to plug in a 0 every single time I see a y. And I'm going to solve for each side of those inequalities. So I have 0 plus 3 will give me 3. And here I have negative 2 times 0, which gives me 0. My inequality seems to suggest that my left-hand side, my 3, should be greater than my right-hand side, which is 0. This is in fact true. So we are going to shade the test point region, which includes my 0, 0. Lastly, I know that it is continuous because, again, no restrictions and there's no word problem, so we are going to shade fully. Looking at this, I'm finding my 0, 0 test point. There she is. And I'm going to shade that side of the boundary line. So I'm going to be really careful when I'm next to my boundary line, and then I don't care as much when I'm further away because I know the graph extends anyways. We just don't have the graph extending on our sheets of paper. And again, we can check with Desmos to make sure that we're accurate so that we know exactly that we're on the right track here. So y plus 3 is greater than negative 2x. And I'll make that a little bit bigger for us to see. And here we have it. So we have negative 3 as our intercept there. Our intercept for x-axis is negative 1.5. And if we look at our graph, that's roughly where ours is. Our line here is dashed just as ours is. And we've shaded the top right portion just like we did. Whoop, whoop, life's good. All right. The last piece of this lesson is just determining if certain points are solutions to our linear inequality. So essentially, this is done in a very similar way in which test points are done. To determine if something's a solution, we plug in the points. We plug in, for example, our first point is 6, 4, and we want to determine if that's a solution to this linear inequality here. To figure out if that's true, we're going to break it up into the left-hand side and the right-hand side. We're going to plug in a 6 every time we see an x. We are going to plug in a 4 every single time we see a y, and see if our linear inequality is true. If it's true, it's going to be a solution. If it's false, it won't be a solution. Okay? So that's going to be your game plan, and we have tons of practice on this page here to check it out. So, for our left-hand side, on our left-hand side of this inequality here, we just have y. Our right-hand side, we have negative 3x plus 2. Now, like I said, we are going to plug in the 6 every time we see an x. We're going to plug in a 4 every single time we see a y. So here we see a y, so we're going to plug in a 4. Here we see an x, we're going to plug in a 6. And we are going to get both sides to give me one final number. So this will give me negative 18 plus 2, which is negative 16. The inequality suggests that for our left-hand side should be greater than or equal to negative 16, which is true. Because it is true, that implies our point, or you know what, I'm going to write 6, 4 is a solution. So if it is true, that point is then going to be a solution. If it is not true, that point is not going to be a solution because it doesn't belong in my solution set. Same thing for this one here. We're going to split it up into left-hand side and to our right-hand side. My left-hand side is just y. My right-hand side is negative 3x plus 2. Right? We get that from the inequality given to us up above in the question. This time around, we are going to plug in a negative 1 every time we see an x and a positive 8 every single time we see a y. So here for my y, that becomes an 8. Here for my x, I get a negative 1. And that becomes a 3 plus 2, which is a 5. My linear inequality suggests that my right-hand side should be greater than or equal to my left-hand side. So is 8 greater than or equal to 5? That's another true statement. So here we have the point negative 1, 8 is in fact a solution. Yay! are going to continue on with these next 4 examples, and they are done in the exact same way. So we are going to look at our points, for example, 4, 2. We are going to break up our inequality into a left-hand side and a right-hand side. We are going to plug in 4 every single time we see an x. We're going to plug in 2 every single time we see a y, and see if our linear inequality is in fact true. What I am going to suggest is that you go ahead, pause the video, try the next 4 on your own, or at least the next 2, check your answers, and the next 2 after that. There is no other trick, there is nothing new, nothing changes, but just for more practice, if you could try this on your own, that would be absolutely wonderful. What we can do, actually, which I think is kind of cool, is if we look at Desmos, come on Desmos, is if I plug in that inequality, y is greater than or equal to negative 3x plus 2, and I decide to plot my point, say I want 6, 4, notice that point belongs inside my solution region, right? It's part of that shaded area that represents my solution set, and therefore it's a solution. I could do the same thing with negative 1, need my bracket here, negative 1, 8. And that is also within my solution region. So I could see both of those are solutions as they both belong in that shaded solution region of my graph. All right, next one here. Here we have this next inequality, so y is less than 1/2 x minus 3. So I'm going to split that up just like I have before. Left-hand side, right-hand side. My left-hand side is y. My right-hand side is 1/2 x minus 3. When I plug in values for this point, I'm going to plug in a 4 every single time I see an x. I'm going to plug in a 2 every single time I see a y. So here, I see a y, I'm going to plug in a 2. I see an x, I'm going to plug in a 4. My left-hand side is all done and reduced. My next right-hand side, it's 1/2 times 4, which gives me 2. And 2 minus 3 is a negative 1. Here, we are double-checking and saying, hey, is 2, my left-hand side, is that less than negative 1? And no, of course, that is false. So 4, 2 is not a solution. So if that inequality proves to be false, then that's going to say, no, it is not a solution. We have the next one here, different point, same inequality. We're going to break it up into left-hand side and right-hand side. Our left-hand side is y. Our right-hand side is 1/2 x minus 3. This time we are going to plug in a negative 2 every single time we see an x. And we're going to plug in a negative 10 every single time we see a y. So here we have y, so we're going to plug in a negative 10. And on this side, we have a negative 2. The right-hand side is not fully simplified. 1/2 times a negative 2 is going to give me a negative 1. And negative 1 minus 3 will give me negative 4. Again, my linear inequality seems to suggest that negative 10, my left-hand side, should be less than negative 4. That is in fact true. So negative 2, negative 10 is a solution, right? Because it makes the inequality accurate. And again, we could look at Desmos and we can see if we get the same result. So we'll plug in our inequality. Y is less than 1/2 x minus 3. Then we have the point 4, 2. 2. And notice how it's not in our solution region. It's not part of the shaded portion of our graph, which means it's not a solution, and that's exactly what we got on our algebraic solving of our solution here. And we could still look at our next point. So negative 2, negative 10. And that point is in fact part of our solution region. It's part of that shaded area of our graph, which makes it oh so nice and a solution, which is exactly what we got as well. This last example, if you haven't paused me yet, I would absolutely love it if you could pause me now so that you can double check that your answers are as accurate as possible and you know how to do this on your own. Okay? Go ahead, pause it, do what you gotta do, and then come back once you're done. Once you've done these two examples so we could verify that we've got the same thing. All right, I've assumed you've paused, you're coming back now, life is great. We are doing things just as we always have, except this time we have a new linear inequality and some new points to go along with it. Here we have my left-hand side and my right-hand side. Oops, right-hand side. My left-hand side is 3x minus 4y, and my right-hand side is just straight up 15. My left-hand side, every single time I see a x, I'm going to plug in a 5. Every single time I see a y, I'm going to plug in a 0 because that is what my point is suggesting. So I have 3 times 5 minus 4 times 0, which gives me 15 minus 0, which is 15. My right-hand side is done and completed. I have nothing that I need to do with it. Life is good. So I'm going to double check that my inequality is accurate. So it suggests that my left-hand side, my 15, should be greater than my right-hand side, which is also 15, but it's not greater than, they're equal to, and that's not what the inequality suggests. So this is false, which means my point, my 5, 0, is not a solution. Okay? We have one more left to go, and then we'll be done. So let's try this one here. So we have our left-hand side and our right-hand side. Our left-hand side, again, is the same. It's 3x minus 4y. Our right-hand side is our 15. With my left-hand side, this time I'm plugging in a new point. So an x, or a negative 2 every time I see an x, and a 3 every single time I see a y. And here I have 3, and I'm going to go times negative 2, minus 4 times positive 3. Which gives me negative 6 minus 6. Oh, sorry, negative 6 minus 12, which gives me negative 18. And similarly, my inequality suggests that my left-hand side, my negative 18, should be greater than my right-hand side, which is 15, which is again false. Since it is false, that implies that negative 2, 3 is not a solution. And again, we can check with Desmos just to ensure that we're not crazy psycho people. So we have 3x minus 4y, and that should be greater than 15. And now we're going to plot our points. So we had the point 5, 0. And notice how it's right on that boundary line, but that boundary line is dashed, which means that any point on that line doesn't get included, which means it's not a solution, just as we had indicated earlier. Our second point, if we go back here, our second point is negative 2, 3. And again, that is just right out of our shaded solution region, so that is also not going to be a point that is a solution to our inequality. All right. We have some 6.1 homework, which involves graphing the inequalities, and we have 4 of those that you have to graph. Oh, just kidding. 6 of those that you have to graph, but you can do it. All right, give it a go. If you have any questions, feel free to message me over Teams. I'll be as helpful as possible. Feel free to watch this video as many times as you want.